Hi, it's Double O Pi, your undercover chemist here. Today we're going to be talking about integrated rate laws. Specifically, we're going to talk about how to derive integrated rate laws and how you use integrated rate laws to determine rate orders from experimental data. So, quick review. If you have a reaction with reactants A and B forming products, it doesn't really matter what those products are, you can express the rate of that reaction as some constant, K, times the concentration of A raised to some power, which we're going to call M, times the concentration of B raised to some power N. Now, when we write the rate law in this form, we call it a differential rate law, which you will understand in a little bit, assuming you know calculus. For the remainder of this video, we are going to talk about a one reactant rate law. And the reason we do that is because if there's more than one reactant and we are trying to determine the rate order of that reactant, we keep the concentration of the other reactant constant and only change the concentration of the first reactant. And so we can just assume that the second part, the part with the concentration of B, is going to remain a constant, and we lump that in with the rate constant K. Let's go ahead and start by talking about a first-order reaction. And we start with first-order reactions because those are the most common that you'll see in the lab. So remember, for a first-order reaction, the rate is equal to the rate constant K times the concentration of A to the first power. Now, what is the rate? The rate is how the reaction changes with time, and we can express that as a function of how the concentration of A changes with time. So the concentration of A is going to decrease over time, and the rate of the reaction is going to be a positive rate. So we can rewrite the idea of the rate as the change in concentration of A over time, and that is going to be equal to rate constant times the concentration of A. I've simplified away the exponent 1. So now you see why this is called a differential rate law. We're talking about rates of change, but sometimes it's really helpful to have things in terms of just plain concentrations, not changes in concentrations. And so what we want to do is we want to integrate this. Before we do that, we need to do some rearrangement here. So now we have rearranged things so that every term with concentration of A is on the left side of the equation, and everything that doesn't have the concentration of A is on the right-hand side of the equation. And now we can integrate it. We're integrating from time 0 to some random time t, and we'll talk more about that in our next video, what that time t means. If you do that integration, you come up with this integrated rate law for a first-order reaction. Natural log of the concentration of A at time t minus the natural log of the concentration of A at time 0, which is your starting concentration, by the way, equals minus kT. You'll sometimes see that written in the form that you see down at the bottom of the page, natural log of the ratio of concentration of A at time t to concentration of A at time 0 equals minus kT. That's the same equation that incorporates a property of logarithms. But now let's look at how we use this integrated rate law in the laboratory. I have rearranged that rate law just a bit, and the reason I've written it in this form is because this is the form of a line. So you can see that here we have a line where y is the natural log of the concentration of A. The slope of the line is minus the rate constant. The x-coordinate of this line is time t, and the y-intercept is going to be the natural log of the concentration of A at time 0. So if we have experimental data and we want to find out if it's a first-order rate law, we're going to graph the natural log of A on the y-axis, and we're going to graph t on the x-axis, and the slope of this line will be negative k. So here's an example of some experimental data. We have natural log of A here on our y-axis, we have time on our x-axis, and our slope, which we can see here from our linear fit, is negative 0.0034, which means that k, our rate constant, is 0.0034. Now let's look at second order reactions. For a second order reaction, the rate is equal to the rate constant k times the concentration of your reactant squared, or raised to the second power. Once again, we'll write our rate as the change in concentration of A over time. And we're going to rearrange this once again so everything with the concentration of A is on the left side and everything else is on the right side. And now we're going to integrate from 0 to t. Again, we did this exactly the same way we did the first order equation, except it's a slightly different rate law. When we do this integration, we get the integrated rate law for a second order reaction. You can see there's a difference in that instead of having natural log of A, we have 1 over A. Let's rearrange it just a bit. Will give us the form of a line. So here's our y, 1 over the concentration of A. Our slope is going to be k. Our x-coordinate is going to be time. And our y-intercept is going to be 1 over our starting concentration. So again, if you have experimental data and you want to see if it's a second order rate law, you can graph them with 1 over the concentration of A on the y-axis, time on the x-axis, and if it really is second order, the data will form a line whose slope is the rate constant. And here you can see what this looks like for a second order equation. Our slope of the line is k, and it is, in this case, 0.0033. Now let's do a zeroth order reaction. Remember, a zeroth order reaction is one where the rate is the rate constant times the concentration of A raised to the 0th power. We could simplify that quite a bit and just say the rate is equal to the rate constant. So once again, we're going to go through and write the rate as the change in concentration of A over time, and that equals the rate constant. Let's rearrange things and integrate from 0 to t, and what we get is this equation. Again, this is different. Instead of having natural log of concentration of A or 1 over the concentration of A, we have just the concentration of A. And we can rearrange this into linear form once again. Here's our y, just the plain concentration of A. Slope is minus k. Time is going to be our x-coordinate. And our y-intercept is going to be the initial concentration. So if you have experimental data and you want to see if they're following a zeroth order rate law, what you're going to do is you're going to graph concentration of A on the y-axis and time on the x-axis. And if it's zeroth order, you should get your points forming a line whose slope is negative k. So let's look at a graph. Here we have concentration of A on the y-axis, we have time on the x-axis, and we have a bunch of points forming a line whose slope is negative the rate constant. So our rate constant here is 0.0008. So if you have to do an experiment and find the reaction order, what you're going to do is you're going to go through and you're going to graph your data 3 different ways to see whether something is zeroth order, first order, or second order. So zeroth order, you remember, is concentration of A versus time. First order is natural log of A versus time. And second order is 1 over the concentration of A versus time. And you're going to compare these graphs and see which of them is the most linear. Now, in this case, it's pretty obvious. For the zeroth order, we have a pretty curvy slope. And then we have an upward slope for the second order, upward curve. And only first order is remotely linear. So for this particular instance, it's obvious we have a first order equation. Unfortunately, it's not always that straightforward. So here I have some other data where we have everything graphed on one graph here. So here we have our zeroth order are the blues. That's the concentration of A versus time. We have the second order, those are the reds. That's 1 over the concentration of A. And then down at the bottom we have the natural log of A, so that's going to be our first order reaction. Is this a zeroth order, a first order, or a second order reaction? When you look at it, you can't really tell. They all look kind of linear, don't they? How do you determine which of those orders is correct? The answer is you use the linear fit on Excel. And you put a trend line in and you look at not only the slope, but also the r squared. The r squared is a value that shows you how linear something is. So the closer you are to 1, the more linear you are. So here we have, if you look at the bottom, our first order green points. Our r squared is 0.98. That's really fairly linear. Our zeroth order points, if you look at the r squared, those are the blues in the middle, that r squared value is 0.94. So that's less linear than the first order. So it's not zeroth order. Now if you look at the top data, you can see that the r squared is actually equal to 1, and so that is the most linear of all the data sets. So this is actually a second order equation. If you get data that's really close like this, one of the best things you can do is to get data points that are really far out in time. So in this case, it's still linear out to 450 seconds. So you might want to take a data point at maybe 1,000 seconds, and at very distant times, you start to see a very big difference between the zeroth, first, and second orders. So, quick summary of how to find the reaction order experimentally. Measure your concentration of A at different times, and make graphs, 3 different graphs of concentration of A versus time, natural log of A versus time, 1 over concentration of A versus time. Find the plot that's the most linear. That represents the reaction order of the reactant you're examining. Thank you for watching this video. Please check out the other problem-solving videos from Double O Pi Productions. We will have more kinetics videos coming soon, and we have quite a few other videos as well.